The next processing method we will be considering is compression molding. This is another process where a ready-to-mold sheet is used. It's compressed by moving mold, and cooling also is facilitated by high temperatures in compression molding process. And we can summarize main features of this manufacturing technique. It's used in automotive industry. This process has high volume capabilities, and certain large automobile panels can be produced by this method. Main raw materials, or the main raw material, is the SMC, that is sheet molding compounds. Bulk molding compounds are also used in compression molding processes. And this process is similar to the stamping process. Stamping is on metals, but this process works with polymeric materials and fibers. There is a video demonstrating this manufacturing process. I can show you, I can play this video, I think. Let me open the file. That is an illustration of this procedure. Okay, that was the compression molding procedure. The final product contains a certain amount of fibers. There are two molds here, a fixed mold and a bowing mold. The sheet molding compound are displaced on the lower mold, and it's cured and consolidated by the help of the moving mold. We can talk about main characteristics or features of this technique. These are some other parts processed by compression molding. These are heavy track composite parts. This component is used in B-22 Osprey helicopter and other composite structure. Basic processing steps are outlined here. Raw material is SMC, sheet molding compound, and it's placed on the lower mold. This is the female mold head, or the lower mold, and the male mold head is moving. You place a certain amount of SMC, it's cut and placed on the male mold head. This is also called charge, SMC or BMC. Its exact size and shape is calculated because after compression, this piece of ready-to-mold sheet has to fill in the cavity between the molds. And that's the shape of the final product. There is a certain amount of flow here. And at this position, it's heated because the molds are preheated to their temperature is increased to a sufficient level. It could be 140 degrees Celsius. And pressure applied on the charge or sheet molding compound facilitates consolidation. And the product is cured. It stays at this configuration for a certain amount of time. It's generally between 1 minute and 4 minutes, 3-4 minutes. The upper half is closed rapidly. The speed of the upper half is given here around 40 millimeters per second. And this motion causes the charge to flow inside the cavity, shown here. Curing time is between 1 and 4 minutes. And at the end of the process, the part is demolded using ejector pins. And they mold. These are ejector pins. And they allow removal of the part from the mold. Raw materials are known. We have talked about SMCs and BMCs. They contain viscous or short fibers, a filler material, and resin material. SMC is in sheet form, BMC is in log form or rope form. They are B-staged raw materials. Thus, final curing takes place during compression molding procedure. The fiber amount is not as high as that found in prepreg reinforcements. Application of heat and pressure, we have already talked about this or shown this. The molds are preheated either by circulating steam or electrical cartridge heaters. And the pressure is due to the moving upper half of the mold. And by means of this moving mold, a preheated mold halves, the curing and consolidation steps are performed, and in the end, solid components, composite components, is produced. Main advantage is the high volume characteristic of this method. Automotive applications require high volume processes, and for this reason, certain components used in automotive industries are processed by these methods. The raw materials are generally low-cost components. SMC is a low-cost component. It's not as expensive as prepreg components. Surface quality is generally at a satisfactory level. Additional processes are not generally required to improve surface quality of these components. And the limitation, there should be a certain amount of investment for equipment and mold. There are two parts of the mold. One of them is moving. And in the design, there should be a certain way of design for heating of these molds, preheating. It's not suitable for prototyping. It's not suitable for low volume manufacturing. Number of components produced should justify the investment on the equipment. And the parts produced are not generally structural parts. What do we mean by structural parts? The parts produced by compression molding are not generally structural. Their strength and stiffness cannot be as high as those of prepreg laminates. But still, there is a certain degree of reinforcements, and the parts can withstand certain levels of applied stresses. These are the main drawbacks or limitations of compression molding. In compression molding, ready-to-mold sheets have to be used. The fibers are not directly impregnated with resin material, liquid resin material. Next two manufacturing processes, in the next two manufacturing processes we will be talking about, the fibers are directly integrated into the resin mixture. These materials, or these manufacturing methods, do not employ ready-to-mold sheets like prepregs or sheet molding compounds. And the first method we will consider is called filament winding. It's based on use of filaments. A filament is a single fiber, but bands of fiber are used in filament winding. Groups of fibers are wound around a mandrel or a shaft, cylindrical body. And there is a carriage unit in filament winding. This carriage unit, the fibers are attached to the carriage unit. And this unit moves back and forth, while the mandrel, shown here, is rotating about its own axis. And by controlling the motion of the carriage unit on the mandrel, the desired fiber angle is generated and fibers are wrapped around this cylindrical body, which is also named as a mandrel in filament winding procedure. This is particularly useful to produce composite pressure vessels or tubular parts. the methods we have been considering up to this point are not really that useful to produce pressure vessel structure, or closed structures can be produced by the filament winding process. And these are some components that were produced by filament winding. These are slide bearings. And they are reinforced by bands of fibers, which are visible here, probably glass fibers in thermoset resin. Reinforced pipes can be produced as well as pressure vessels. These are filament woven reinforced pipes. There's a certain amount of fiber angle as shown here. There is another demonstration of this process. I'm going to show this never video actually. Let me open this. Let me share this file. That was a demonstration. And we can talk about main characteristics of this process or basic processing steps. Fiber yarns are used. They are twisted fibers. Spools of yarns are shown here. Then they are passed through a resin bed. This contains liquid resin mixture. Hardener filler materials are included in this resin mixture. So there's the carriage unit. It is under linear motion. And the fibers go through the pair-out eye here. At the same time, this mandrel is rotating and the fibers can be wound around this rotating mandrel. Once the sufficient or required thickness is produced, the process can be stopped. Additional fiber tension could be necessary in the process. This is created by a tensioning device. This is for better consolidation of layers of composite cylindrical body. And once this is completed, it could be necessary to cover this with a shrink tape or a bleeder plastic material. This facilitates the formation of a better surface finish. This shrink tape contracts during curing, and it helps create a better surface finish at the outer surface of the cylindrical body. For curing, the mandrel and the composite cylindrical body can be moved to a separate room or an oven, and curing has to take place generally at an elevated temperature. It's possible to do it at room temperature as well, but this accelerates the curing process. And then once this is complete, the mandrel can be removed. There are certain applications, there could be certain applications where the mandrel is an integral part of the composite structure, but generally it's removed. This is the summary of filament winding procedure. Any questions or comments on this part? raw materials are already described. Continuous fibers are the raw materials here, and they are in yarn form. Simple liquid thermoset resin mixtures are used. Any type of fiber is possible. Glass, carbon, or Kevlar fibers are commonly used here in filament binding procedures. Again, epoxy is the main material. Polyester and vinyl ester are also used as resin materials. The tool is the steel mandrel here. They could be chrome plated for improved surface finish on the part of the composite structure. Other mandrel materials are possible. One of them is aluminum. And in certain applications, the mandrel is an integral part of the composite structure. Heating is again needed for cooling. This takes place generally in a separate room in an oven. Additional heating is possible by ultraviolet curing or electron beam curing. And these are performed during the process itself. We don't have any external means of pressure or vacuum type of pressure application. Simple tensioning devices can be used to have sufficient amount of fiber tension over the underlying composite structure. What are the advantages? Certain type of structures can be produced by this technique. This includes pipes, composite pipes, pressure vessels, bearings. This is the only technique available to produce such round parts. The process can be automated. It's possible to use this in high volume production. And raw materials are generally low cost materials. You don't need any prepregs, fabrics, simple filament type fiber materials are used. So it could result in cost effective composite structures. And what are the limitations? Closed structures can be produced. It's not possible to fabricate open structures like bed tops. And the fiber angle, there is a limitation on the fiber angle. The fiber angle is the angle between the fiber and the horizontal. It's around 45 degrees most of the time. And this leads to reinforcement in both longitudinal direction and the circumferential direction. You have a certain degree of reinforcement in the hoop direction and the longitudinal direction. But you cannot increase the reinforcement in the longitudinal direction any further because really low fiber angles are not generally possible. So you cannot make it zero. Therefore, there is a certain limitation on the winding angle. Maximum fiber volume fraction is generally less than 60%. In prepreg production, you can exceed this fraction, but there is a limitation on the fiber volume fraction, maximum fiber volume fraction in this process. And that could be problems associated with the uniformity of fiber distribution because bands of fibers are used a group of fibers are wound in this region, then another group in this region, and there could be a certain range or a cylinder, but there are no fibers. So this is related to the uniformity of the process. Any questions or comments on filament
Bir şey
binding?
sorabilir miyim?
Yes.
Derste yoklama alındı mı acaba?
I'll take it later at the end of the lecture. Now, one final processing method is pultrusion. Again, this does not make use of ready-to-mold sheets, but you can use fibers, rowings, sometimes fabrics as well. As the name implies, the fibers are pulled to a die. There is a heated die here, and a fiber resin mixture is pulled to this heated die by a pulling unit. Die has a certain cross-sectional shape. It's generally a tubular structure. Both circular and rectangular cross-sections are possible. Die, therefore, applies the required pressure for consolidation, and it's heated for curing of the resin. And after this passes through the die and cured, it can be cut by a saw, cutting saw here to the desired length. We have another demonstration here. I think it could be useful to watch this demo on Pultrusion. I'm going to open this file. That was a simple demonstration of pultrusion process and what are the main characteristics of this method. These are some samples, sample pultruded profiles. That could be square or rectangle cross-sections or open cross-sections like this. And these are pultruded tubes. All of them are reinforced in longitudinal direction. Basic processing steps are shown here one more time. These are glass rowings, and it's possible to add matte type fiber reinforcement as well. And there is the resin impregnator here. There's the resin mixture. A surfacing wheel can be used to avoid excessive damage due to abrasion, wear, friction. The mixture is pulled to this forming die. It's heated for curing. This is the pulling system. This applies the required force. Finally, reinforced product can be cut to the intended lengths. That is a summary here. And what are the raw materials? As we have already mentioned, unidirectional fibers are the common raw materials for this process. Could be glass, carbon, or aramid. Woven fabrics or mats can also be used as the raw material. If these are used, then the reinforcements could be bidirectional instead of longitudinal. Polyester is B-staged polyester is a common resin material here. Monoesters and epoxies, again, are thermoset materials. And there are a certain amount of fillers and additives which improve certain other characteristics of the thermoset material. The tooling is the die. This is generally a steel die. This converts the resin impregnated fibers to the intended shape. It's always constant cross-section application. They are heated. Wear, abrasion, and friction could be a concern here, and the tools are re-chromed to minimize damage due to wear on both the die and the cylindrical body itself. There are no external sources for consolidation. The die compacts the fiber resin mixture. They are compacted while being pulled through the die opening, but die has to be heated for curing. And that could be a dwelling time. It depends on the characteristics of the resin, but it has to be heated. The composite structure has to be heated for complete curing. What are the advantages? It's a high volume process. It's suitable to produce high volume composite parts. It's a continuous process. Raw materials are not ready to mold sheets. They are generally simple fibers. When bidirectional properties are required, the raw material could be a woven or non-woven fabric as well. It's possible. Limitations. Tapered and complex shapes are not dealt with in this process because the dies generally have constant cross sections. So you may refer to a different process, or you may need to design a different procedure for more complex shapes or tapered shapes. It could be filament winding or some other kind of method. The parts produced are not generally high tolerance parts because of the nature of the pultrusion process. It's not intended for thin walled parts. If the part is really thin, it could be damaged while it's being pulled through the die. There's a certain limitation on the lowest wall thickness. If you use continuous reinforcement, fiber angle is limited to 0 degrees. This is the fiber direction. You might use glass rovings or yarns. Then the body is going to be reinforced in this direction. It's going to have a higher strength and stiffness. But in the other direction, in the circumferential direction, the properties of the epoxy will be more dominant. If in the actual application, the stresses are longitudinal, then there won't be much problems. But if you have stresses in other directions and there is internal pressure, this is not, of course, suitable. But fabrics, woven fabrics, bidirectional fabrics can be used to circumvent such problems. So it's possible to have improvements on the process itself. Any questions or comments on this technique or procedure? All of the methods we have mentioned up until this point were on thermosets. Thermoplastics are also used in composites manufacturing. They are not as commonly used as thermosets, but there is an industry on thermoplastics as well. And similar techniques can be applied for thermoplastic composites, including filament winding, pultrusion, compression molding, clay processing. We have talked about all these techniques, but other techniques such as injection molding, diaphragm forming processes are also possible. I may read the parts pertaining to thermoplastics as described on composites manufacturing book that is available in the references. But this is the end of our discussion on composites manufacturing. Starting next week, we will consider mechanics of composite structures. How are composites modeled? Which methods, mathematical techniques are needed to calculate stresses in composites? Or as a material, how we can model a composite, because a composite's body is not a standard isotropic homogeneous body. First of all, a composite is not isotropic. It has different properties in different directions. Secondly, it's not actually homogeneous because it has both fibers and matrix material. How you can model the composite behavior? The first question is, how is the material behavior model? What kind of constituent relations are used in modeling of composites? Hooke's law, but a different version of Hooke's law is needed, which accounts for the anisotropy of composite structures. And if you have the correct material model, you'll be able to compute the stresses in a single lamina consisting of fibers and matrix material. The second question is, how can I find material properties of composites? You have a certain margins of elasticity, for example. In a pultruded component shown here, there is a certain margins of elasticity in the longitudinal direction, but a different margins of elasticity in the circumferential direction. And how can I find these margins values? Or how can I develop methods to predict the material properties? Micromechanics, this is called micromechanics, and it's an important component of composites analysis and design. And the third question is, how can I examine laminated composite bodies? In prepreg layer, you have a number of prepregs. Fibers can be oriented in different directions. In the first prepreg, the fibers could be in longitudinal direction. In the second prepreg, they could be oriented in the orthogonal direction. And we have a number of such prepregs or layers or plies. How can I extend the methods for layers to examine such composite structures? All of them, or all of these problems will be dealt with in the remaining part of the course. If you don't have any questions or comments, that's the end of the lecture for this week. And we will start talking about analysis of composite structures next time.